Up to this point, when we've been integrating, we've been able to find a family of functions that have a certain derivative. That is to say that if we were, or when we integrate, say, x squared dx, we end up with 1/3 x cubed plus c, where this constant of integration can represent anything. Right? There's a group of functions that all have the same derivative. But we can, given the right information, figure out what the constant of information is, and then we'll have a specific answer. All right, which of the possibilities in the family actually function here? And so when we're solving these kinds of problems, these are ultimately called differential equations. These are just equations that are the derivative of something. And the solution to a differential equation problem is just another equation. So if you're solving a differential equation, you're going to find an original function, or a function with the given derivative. Right? So for example, let's consider f prime of x, the derivative of f, is equal to 3x minus 1. And we're told one important fact about the original function. F of 2 equals 3. Right, so when we substitute 2 into the original function, we need to get 3 out of it. Well, when I integrate f prime of x, what I'm going to find is the original function. I'll get f of x, and f of x plus c in this case, because we won't have any way of drilling it down. Now, more importantly, since f prime of x is 3x minus 1, when I integrate that, I'll get 3 halves x squared minus x plus c. But one thing I know about this is that when x has the value of 2, the entire function needs to be equal to 3. And with just that one known point, I can solve for c. So this will be 6 minus 2 plus c equals 3. And that means that c is equal to negative 1, which means the solution to my differential equation, or my original function, must be 3 halves x squared minus x minus 1. So by just knowing one point, I can actually figure out which function I'm working with. Let's consider a few more examples. In this case, f prime of x equals x squared minus 2x plus 2, and we're told that f of 3 is equal to negative 1. So the integral of x squared minus 2x plus 2 dx, well, that's equal to 1/3 x cubed minus x squared plus 2x plus c. But when x has a value of 3, then the whole thing needs to be equal to negative 1. So now I can solve for c. 9 minus 9 plus 6 plus c needs to equal negative 1, which means c must equal negative 7. So the solution, f of x, is 1/3 x cubed minus x squared plus 2x minus 7. Let's consider another example. In this case, we're given the second derivative, so better get some more room. So in this case, I know that the second derivative of x is equal to 2. I also know that the derivative when x is 4 is equal to 1, and I know the original function when x is negative 1 is equal to 2. So I'd like to solve this by finding the original function. So in this case, the integral of 2 dx is 2x plus c, right? And that must be f prime of x. But I know that when x has the value of 4, then the derivative is supposed to be equal to 1, which means that c should be equal to negative 7 in terms of the derivative. This means since my derivative is equal to, what's this equal to here? Two x minus 7. Then what needs to be true is that when I integrate this with respect to x, I should get the original function. So in this case, that will be x squared minus 7x plus c. And I know that when x has the value of negative 1, then the original function has to equal 2. So this means that c has to equal negative 6. So the original function in this case is x squared minus 7x minus 6. Two more examples involving some differential equations. In example 21, I know that the second derivative is equal to 2x. I know that when the derivative has an input of negative 5, it will be equal to 30. I know when the original function has an input of 2, it will be equal to negative 1. I'd like to find the original function. Well, the integral of 2x dx is x squared plus c. And I know that when in the derivative the input is negative 5, the output should be 30. This means that c should equal 5. So I know my derivative is equal to x squared plus 5. If I integrate the derivative, I should get x squared plus 5 dx. I should get something related to the original function. This would be 1/3 x cubed plus 5x plus c. But I know that when the input is 2, then the original function should be equal to negative 1. So, let's see, 8/3 plus 10 plus c should equal negative 1. That's an interesting number. This means that c will equal negative 41/3. So my original function and the solution to this problem should be 1/3 x cubed plus 5x minus 41 over 3. There's one final example, and that is, we're told that the graph of a function passes through the point 1, 6. So 1, 6 is a point on f of x. And the slope of its tangent line at x f of x is 2x plus 1. So what this means is that at any given point, the slope of the tangent line, or the derivative, is equal to 2x plus 1. And what we want to know is, what is f of 6? So if I knew what the original function is, then I could figure out what f of 6 is. Well, I know that if I integrate the derivative, I'll get something related to the original function. In this case, it would be x squared plus x plus c. And I know that when x is 1, the original function has a y value of 6, so this means that c must be 4. So my original function must be x squared plus x plus 4. And since I want to know what f of 6 is, I'll just substitute 6 in, and that'll be 36 plus 10, which is 46. So I just had to interpret the question, and I was able to answer it. There's a lot of different examples for indefinite integration.